Hello again. Here in this lecture, we're going to continue talking about random forest models, but rather than think about the overall accuracy of our predictions, we're going to look at what the model tells us about which factors are important in those predictions. So what are the factors that are most strongly associated with, again in our example, the presence of an accessory dwelling unit on a parcel of land in Los Angeles. So we're going to look at feature importances in particular, which are one way to assess that, and explore the use of partial dependence plots, which you may be familiar with in a regression context. The intuition is exactly the same. So let's recreate the same random forest model as before. This code is in your GitHub repository, follow along, and we've seen all of this before. We're loading in the data, creating dummies, drawing the data frame, specifying our variables, creating the subset of the columns and dropping the NAs, creating the train test split, and then estimating the model and our predictions. So all of this code you've seen before. This is a nice refresher to make sure you can go through each line and understand exactly what it can do, so you can replicate it in your own examples. If you have a regression model, then the size of your coefficient and the sign of your coefficient are good guides into which variables are important. So what does that look like in a random forest setting? Well, the equivalent concept is feature importance, and it's often measured something called mean decrease in impurity, or MDI. And don't worry about, for our purposes, what that means precisely, but basically it means how much does a variable improve our predictions. Now these importances are accessed from the feature importances property of this RF object. Remember, this RF was what we created as our random forest classifier. And there's some good examples on the scikit-learn documentation that show how to evaluate the importance of features. And we're going to use very similar examples to that website. So I took some of the code snippets from right there. So let's import our libraries. And we'll store these feature importances in an object we're going to call importances. Let's convert it to a pandas series. It's like a one-column data frame, and tell it what our indexes, our column names are. Well, these are the labels from our xtrain data frame. And then we're going to want to plot error bars, and we can do this through calculating the standard deviation across all of these trees. Remember, RF estimators, we had one of these for each of our trees. And so we're going to look at the feature importances from each of these trees, and then look at the standard deviation across all of them. Again, this code I took from the scikit-learn documentation. And then let's plot them. So what does this look like? Well, a mean decrease in impurity is a measure of importance. All this plot really tells us right now, because there's so many features we're plotting, is a lot of them are really important and a lot of them aren't important at all. So what can we do? So we could make a larger plot with horizontal bars, and that means the text will be easier to read rather than cramming in them in vertical bars, and so the x-axis is compressed. We can have more space if we go vertical. We could only plot the most important features, or we could use an interactive tool that you hover over the bar, and Plotly and NPL cursors. Those are two libraries that give you really nice interactive plots where you can hover over things in a Jupyter notebook. But let's try this first option. Let's try the horizontal bars. So let's use Seaborn rather than Matplotlib, which can generate, in general, prettier plots. Let's sort them by descending order. So our most important features, again, those that have the most predictive accuracy, are going to be at the top. And then let's do a bar plot rather than which will be horizontal. And our x-val are going to be the values of these importances, and the y are going to be our column names. And we'll plot it on the axis that we created here. And let's tell Seaborn what the titles should be. So this is much easier to interpret, right? And we see that there are only a few factors that are driving our results. in particular the improvement value. So basically how much of a building's on your lot worth. The location turns out to be really important. Perhaps we have clusters of ADUs, or ADUs are only built in certain parts of the city. The size of the dwelling seems to be really important. If you have a larger house, perhaps you have more land, you're going to build an ADU as well. The year built, the land value, and some other of these features are important. Whereas most of these dummy variables actually aren't that important. And these are the ones that we took from the classification. Whether you're a dairy farm really isn't driving the ADU, presumably because if you have a dairy farm, then some of these other variables, perhaps the location, but also the square footage of your buildings are going to be much different. So we can see that the value of the land, the improvements on the lot, the location, and the size and year built are the most predictive factors. Now, one way I suggested would be to make this easier is to only plot some important features. So pause the video here and see if you can redo this plot here, but cut it off at 10. See if you can do that for yourselves. Okay, how would I do that? Well, let's just take the first 10. So rather than plot all of them, our x values are only going to be the first 10. And the same for our index. Let's just take the first 10. And so we get a bar plot. Maybe it's a little too big. We should probably make this smaller. Let's change the figure size. And we get a perhaps more comprehensible bar plot without all these extraneous variables. Or you could say you want all of them in your bar plot so that your reader shows or sees that most of these are not important. So these feature importances are very useful in highlighting which variables have a large impact on your prediction. But it doesn't tell us what direction. If you have a larger lot or a larger building, does this mean you're more likely to have an ADU or less likely to have an ADU? It's not clear directly from these forest importances. Well, there's several ways to examine directionality. One approach is called SHAP plots, and there's a really nice explanation here. These bee swarm plots take a little more effort to interpret, but are very powerful in terms of analyzing the impact of a particular feature. You can look at an example of these in my recent paper with Nazanin Rezai on urban form globally and its impacts on air pollution and access to green space. So SHAP plots are one way to do this. A simpler way to evaluate directionality is what's called partial dependence plots. And basically these show the effect of one variable on your outcome while holding everything else constant. And you can look at the documentation for these plots, and there's some great examples in the scikit-learn documentation. The function we're going to use is partial dependence display. Let's have a look and see what this does. So it looks like that it's going to take three arguments. So our CLF, what's this? Well, it's a classifier. Here they used a gradient boosting classifier. It's another type of machine learning model, but it'll work the same if we had a random forest classifier. Then they want their X data, and then their features, which they just gave numeric values to. So what does it look like here? Well, what's our year built? What's the impact of year built on our outcome? Let's pass the random forest object. Let's pass our X test data. And let's look at the impact of year built. It takes a little while to compute this, but we should get a nice plot. Okay, so it probably took a while for you. This is a slow process, but we get a partial dependence plot. So here we see the probability of an ADU against our year built. And so the probability is actually highest for these older buildings. Perhaps this is a small 1920s building, perhaps on a large lot, and has a higher probability of having an ADU. And in these more recent buildings, particularly in the 60s, 70s and 80s, these are less likely to have an ADU on them, although a slight uptick. It's not clear what's going on there. We can also look at the top 3 features. So this is a partial dependence plot for just year built. Well, let's look at the top 3. Well, what are the top 3? Well, we stored these in importances and we sorted them. So our top 3 are improvement value and lat and long. So let's get the top 3 and pass these to our partial dependence display. So the same as we did before, but rather than just pass 1, the year built, we only pass all 3 of them. And this is going to take quite a bit longer, so go away and make a cup of tea. This is computationally intensive, but when you come back, you should have some nice plots to look at. Okay, so eventually that should have run for you. This took about 5 minutes on my computer, and we see the plots for all 3 of these variables. So we see that for improvement value, there's a positive association between that and the probability of having an ADU. If you have a more expensive house on your lot, you're more likely to have an ADU. Latitude and longitude, there's not a monotonic relationship, right? It comes down. These kind of middle latitudes, there is a lower probability of having an ADU. When you get up here, this is essentially the San Fernando Valley. For those of you who know LA, there's a much higher probability of having an ADU. And we have a less clear relationship for longitude going from east to west across the city of LA. So while the feature importances tell you the size of the variable's impact on your prediction in terms of, like, is this most important compared to the other potential predictors, these partial dependence plots show the direction of a relationship. In some cases that's uniform, it's monotonic. In some cases it might be like latitude where it goes down and then that then comes up. There isn't a linear relationship. So we'll leave this lecture here. The feature importance is a way of showing which variables matter in your model, but they don't tell you the directionality. And for that, partial dependence plots, as well as some more sophisticated approaches that we didn't look at here, like SHAP values, these are very useful in that regard.